Good day everybody. In this video I'm going to talk about rock tunnel quality Q system. So we will start with some introduction and then we're going to look how we can apply it into practice. So this is a very popular rating system. It was introduced some time ago by Barton and colleagues in 1974. So this is more empirical correlations based on the performance of rock walls in tunnels. So this classification system is based on a number of case studies. It's been improved with more case studies, with more details and more data. So now let's see what it looks like. So that will be the formula to estimate the Q system rating. So you will see that in this formula we have value of Q, which is the rating, and then we have six different factors, and they would contribute differently based on their properties. So we're going to start with the first one on the top. It's RQD. So this is very important parameter of rock mass quality. It's called rock quality designation. So that one would measure the fractures in the rock mass. I have a video how to measure it. I'm going to put it in the description. A link will be in the description of this video. So please check that one and see how we can measure RQD of the core samples because this is very important parameter. So next one you will see it will be about the number of joint sets. You will see like most of these parameters, it's mostly about discontinuities, joint sets, because joint sets would affect the overall strength of rock mass. So another parameter is related to the surface roughness. So as you already know that if we have joints and the surface is very rough, which is actually very good because it will contribute to the highest strength, like overall strength of rock mass. So if the roughness it's not very pronounced, it's just like more like smooth, slick-sided surfaces. So you will see that in this case, that will actually decrease the overall strength of the rock mass. Of course, we're going to look at the degree of the weathering of those joints. So, and then we're going to assign a rating, and that will go here as a part of it. And these two one, you will see that the first one, this one, J with small case W related to the groundwater pressure, because water is important in rock mass. Is going to affect the stability of the rock mass, especially if we talk about water pressure. And another factor which is important, it's called SRF. So it's a stress reduction factor. So this will show you the stresses affecting in the rock mass in situ, right? So this is the way that is going to be. And now let's go to the next slide. It's just a little bit of extra information. So you will see that what we can do, we can actually like separate these parameters in three different blocks. So this one, block A, would characterize the block size of the rock mass. So this second parameter will show us what will be the shear strength between the joints. And that third one, this third parameter, it's more about stresses. You will see that we have water pressure there and the stress reduction factor. So in practice, this value of Q can have a very wide range. You will see that it can be like very, very small, 0.001 to more than 1,000. Of course, we would like to see it more like around 1,000, which means that rock mass will have a high overall strength. Okay, now let's look at the example. And then we can see how we can apply it, because each factor comes with a description, and then the description is shown here. So I'm gonna go like one by one, and then you will see how I select the parameters. You will see that some of the parameters, like some of the numbers we select, are a little bit subjective, so it depends on your engineering judgment and your experience, right? If you get slightly different values compared to, for example, what I would choose, it's still okay. As long as you can justify them, it's fine. Okay, now let's look at this example when we have a rock mass which is made of granite, and we have three major joint sets. So overall RQD value it's about 88%, and you see we also have a spacing here. So the spacing is 0.24 meters, so it will be average spacing between discontinuities, those joints. So we have some information about the joint surfaces. It's stepped and rough, tightly closed and unweathered with occasional stains. So that's we will need to know as well. And then what we do also given it's that surface is wet but not dripping. And we're also given some information about unconfined compressive strength. So that will be for the stress reduction factor. And for groundwater condition, we are going to use these numbers. I will show you how we can do that. So we'll know that the tunnel will be excavated at this depth, which is 150 meters below the ground surface. And is there anything else? Groundwater normal high CO2 strengths. Okay, so let's just start with each parameter. We're going to start with RQD. So RQD is pretty simple. So what you'll do is you're just gonna see what RQD you have, 88, and that basically will be the number. So, well, it kind of tells you a little bit of more information about the quality, so it's very good, 88. But what we can do right now, we're going to write that RQD, I'm going to write here on the top, RQD, it's equal to 88. Just the percentage, that will be the number. Okay, next one will be joint set numbers. So number 2, so this one, J with a small case n. So that stands for numbers. So we know that we have 3 joint sets, and that's it, right? So 3 joint sets here. That will give us a number of 9. So I'll write down here that this value is equal to 9. Okay, so next one is going to be joint roughness numbers. So you see that we have different descriptions. Just select which one would be probably the best match to what we have. So to me it will be rough, stepped, and what do we have? Rough, stepped, um, rough or regular undulating. So I'm gonna probably go with this one. So it's not smooth and planar. It's kind of like rough or regular, undulating. So this is where you would probably going to exercise your judgment. If your like answer is kind of close to it, but I'm not sure how it can be close for this one. This is kind of straightforward. But sometimes if you're not sure, then you can go, let's say, if it's between E or F, so you will see which one will be the best match according to your judgment and your experience. And you just need to justify it as well. Just explain why you selected that value. So I'm going to write here that in this case, it will be 3, number here. Okay, so let's go to the next slide. So next will be joint alternation number. It's this one. And J with lowercase a. So it's kind of more like about how weathered it is. You will see that it has table number 1, table number 2, and table number 3, right? So if you're given some numbers about, let's say, friction angle, you can select based on the friction angle, right? And also, if you can also read this description, it's very important because some of the description would include, filling material. So, and the other one, we're just not gonna include anything. So, what we know that we have joint alteration factor. In my notes it says sorry, 1. Okay, so I guess what we're going to look at, trying to find as much information as possible. So we know that that surface is wet, but not dripping. So it will be also probably dry excavation with only minor inflow. So let's see where we can find this one. Unalterated joint walls, surface mainly. So yeah, so this one, the only information I can find that will match what we have. There is not really much given. It says just maybe like not, let's not talk about water yet. Water will be the next number 5. So we'll talk first about how about the alternation. So and here what is important, it's tightly closed and weather it with occasional stains. So it kind of gives you some idea how much it's been weathered, right? So you will see that it's not really like that much weathered. First of all, it says unweathered, and then it only says with occasional stains, which means that the rock may be characterized something like from fresh to slightly weathered material because it has occasional stains. So that's why I'm gonna go with this B, which is unaltered joint walls and surface staining only. So out of all these options that were given, I think this one will be probably the best match what we have. So that's why I'm gonna write here J is equal to 1. Okay, now we're going to talk about water because a next factor it's called joint water reduction factor, right? So it's shown here. So for this case, we are only given some information. We're not given any numbers. Like here, we cannot estimate water pressure because we are not really given much information about if there is a groundwater level or not. So in this case, we're just gonna like look for the sort of like general description. And the general description says that surface is wet but not dripping. So something that, let's see what we can find. Um, Dry excavation or minor inflow, medium inflow pressure, large inflow. Okay, I don't think there will be any inflow of water here because it says just like wet but not dripping. So basically it's kind of like moist surfaces, but there is no water flow. So based on this consideration, I think A will be the best feed that we can find. So then I'm going to write JW equal to 1. It's because there is not really inflow. It's kind of like more like dry excavation thing. So there is not much groundwater, either pressure or just groundwater in general. So that would be the numbers here. Okay, so let's see what is left. I think it's a stress reduction factor. Okay, stress reduction factor. Here you can have like few options again. So this one based on some general information, and this one table B, you see we have numbers here. So that will be a little bit easy if we have numbers because with the numbers we can just estimate what is going on, right? And usually in all these examples, we are going to look at this one. So sigma C divided by sigma 1. So sigma 1, it will be major principal stress, major principal stress, major principal stress, principal stress. And usually it's equal to, in many cases, it will be, or we assume it equal to vertical stress. And this one, sigma C, this one will be strength of rock, strength of rock, strength of rock. So we are given that the strength of rock is 160 MPa. I'm going to write here that sigma c is equal to 160 MPa. So it's just a number given to us, right? If we're not given this unconfined compressive strength, if let's say we are given point load index strength, then we have to change it to unconfined compressive strength, and then this is what we use, right? So just don't make this mistake. And okay, so now we need to estimate the vertical stress. So probably you know that to estimate vertical stress, we will need to know the unit weight of rock times the depth of the rock, right? So in this case, we are given that the depth of the tunnel is 150 meters, right? But we are not given unit weight, so we don't know density or unit weight, right? So in this case, as I previously showed you, what we are going to do is we are going to use this formula to estimate vertical stress. It's 0.027 times the depth, z. And the answer that we are going to get using this formula, it will be MPa. So what I'm going to write here in this corner, it will be this sigma c divided by sigma 1. It's 160 MPa, which is the strength, and divided by the 0.027 times 150 meters. So that will give us 39.5. So now we're gonna come here, look at this column and see where we have 39.5. It should be within this range, which means that this value of stress reduction factor will be 1. So I'm going to write the stress reduction factor is equal to 1. Okay, so I don't have much space to write the formula, so I'm going to just write it here in between. So that Q, I showed you this is the formula. So we already found all the factors. Please play it back and see what RQD numbers and what other factors we have. So I'm gonna look at my notes and tell you what it is. So RQD it's 88 divided by 9. That was about number of joint sets. Then times 3 divided by 1. And then times 1 divided by 1. I hope you can see it. Sorry guys if you cannot see it because there is not much space. I should have probably left a little bit of space on the slide. So that should give us the number equal to 29. So if I do this analysis, this Q system number should be around 29. Of course, yours may be slightly different if you slightly different estimated the factors, but it should be probably within this range as mine. Okay, thanks everybody for watching this. Have a nice day. Bye.